real exam questions. This is question 19 about ultimate limit state in general. In domain 2A, calculate the reduced bending moment, which is mu d, and the relative depth of neutral axis C. And do this for three cases, and the values of C and mu d should be calculated to 3 decimal places. First is for optimal use of materials, second at yielding of the reinforcement, and the third is at maximum bending moment capacity. Start with optimum use of material. This means that the strain in concrete must be to its maximum allowable, and the strain in the reinforcement also to the maximum allowable. So consider a section like this, a concrete section before loading. The maximum strain in the concrete is 3.5 per mil. The point of gravity of the tensile reinforcement is situated here, and this is the strain, the maximum strain in the reinforcement, which is 10 per mil. Now, this line, the yellow line, is now the plane of or the strain diagram of the section after loading. X is the position of the neutral axis or the height of the compression zone. And we recognize this immediately. This is the left border of domain 2A. Then we look at the stresses. We take over the neutral axis, the compressive height of the concrete, the total value of the tensile force in the reinforcement, tensile reinforcement. Then we got the parabola rectangular evolution of the stresses of the concrete. And when you make the integration of it, you become the total concrete compressive strength. The distance between those two is, of course, the lever arm Z. And D, the effective depth, is this depth. And the position of the compressive strength value is delta Gx, with delta G the coefficient of gravity. We know, because we are in domain 2A, the rectangle and parabola stresses are fully developed, so the filling factor C is 0.81 and delta G is 0.416. The strain in the concrete, the maximum strain is 3.5 per mil, and in the field 10 per mil. From this, we can easily calculate the position of the neutral axis, which is X, and X over D is then equal, of course, to 3.5 per mil divided by the sum of the two. It's because this angle is the same as this angle, and the tangents of those two are equal, so this is valid. So X over D is then 0.259, and this is the depth of the neutral axis. Mu D is then the reduced bending moment mu D is then the dimensionless expression of a rotation equilibrium around the tensile reinforcement. And you can see this is the concrete compression strength multiplied by the lever arm. Z is equal to 1 min delta G C. When we fill in the different parameters, we find that mu D is 0.187. Maximum bending moment capacity, we go again to our strain diagram from 3.5 per mil, but this time the plane after bending is doing this. That gives you the maximum bending moment capacity. Now, bear in mind, when you are here, you reach an area of tensile reinforcement equals to 0, which is not possible. Otherwise, you don't have an horizontal equilibrium. So this means, in fact, that it's the limit too. When this is very small, you have almost an infinite surface of an infinite area of steel needed to balance out the compression reinforcement. So this is the effective depth, B. It is the right border of domain 2A. Then we go over to the stresses. We see that the total force in the concrete is approaching zero, and the total force in the concrete is at the distance delta Gx, and the lever arm is Z. So C again is 0.81 and delta G 0.416 because we are in domain 2A. The strains 3.5 per mil and 0 per mil, or approaching 0 per mil. So C, it's clear that X is equal to D. So C is by definition 1, and mu D is then you fill in the different parameters and you find that mu is 0.473. So for simple bending, in the zone, which is the zone 2A, mu goes from 0.187 to 0.473. You cannot have a section with simple bending with a value of a reduced bending moment, like for instance 0.5. That's not possible. And the third case was just yielding of the reinforcement. Again, we take the cross section, the strain in the tensile reinforcement, the strain in the concrete compression zone. The maximum is 3.5 per mil. This is the effective depth. Then we have the plane of, or the strain diagram after bending. And you end up here with a strain which is just yielding the reinforcement. So it means when it's B500, you will have 2.174 per mil. So it's just where the horizontal track of the stress strain diagram starts. Then the axis of the position of the neutral axis. We go over to the stresses. So the stress in the reinforcement is the total surface of the reinforcement of the total area, sorry, of the reinforcement multiplied by 2.174. Then for the concrete, we have the concrete stresses and its position Z and X and delta Gx. We are still in domain 2A, so C is 0.81 and delta G 0.416. Epsilon C is 3.5 per mil, and epsilon S is just yielding. That means it is FYD, the design value of the yield stress of the reinforcement divided by the elasticity modus of the steel, and then divided by 1,000, so we express it in per mil. And C is then X over D. You fill in the different parameters and you got 0.617. And mu D, again, you can calculate it easy with this dimensionless formula. You find 0.371. So this means that for a mu D bigger than 0.371, it's somewhere an area here. It's very dangerous because the steel is not yielding. So you should take care that always mu D must be smaller than 0.371. Now, let's make a summary of the three cases. We have, for optimal use of material, epsilon S is 10 per mil and epsilon C 3.5 per mil. Mu D is then 0.187, and C, the position of the neutral axis, is 0.259. This is C. Then we go over to the maximum bending moment capacity, which is this line, the right-hand side of the zone 2A. epsilon S is 0 and epsilon C 3.5. Mu D is 0.473 and C is 1. And then we go to just yielding of the reinforcement, which is mu D equals to 0.371 and C equals 0.617. So now you have a nice overview of the three most important cases of zone 2A.